Let's consider this TP diagram with the coexistence curve, where above the coexistence curve you have phase 1 and below you have phase 2. And now let's consider a process where we cross this coexistence curve. And we do that at a constant pressure. So at constant pressure we increase the temperature, and at a certain temperature T0 we cross the coexistence curve. There we have a phase transition. All of this happens at a constant pressure, which equals the critical pressure, so the P star, at the temperature T0. And let's consider specifically 2 points on this green line, namely just before the phase transition and just after the phase transition. So let's consider a point here, point number 1. This is a point just before we cross the coexistence curve. So we are still in phase 1. And then point 2, just after crossing the coexistence curve. So we've just done the phase transition, effected the phase transition to phase 2. And let's look at the entropies of the substance at these 2 points, 1 and 2. Well, we can calculate the entropy from the free enthalpy. Remember the nice Guggenheim square? The free enthalpy has as its natural variables temperature and pressure. The entropy is the conjugate of temperature. So we can obtain from the free enthalpy, we can obtain the entropy by taking the partial derivative with respect to temperature. And the arrows in the Guggenheim square are such that you have to take a minus sign. So the entropy is given by minus the partial derivative of free enthalpy with respect to temperature at fixed pressure. Since at point 1 we are still in phase 1, we have to use the free enthalpy for phase 1. That's why I write G1. We learned last time that there's a very simple formula for the free enthalpy. The free enthalpy is given by number of particles times chemical potential. The number of particles is fixed. It doesn't depend on temperature. So when we take the partial with respect to temperature of the free enthalpy, then we treat the number of particles just like a constant numerical factor. And all we have is the partial derivative of chemical potential with respect to temperature. So we can say that this equals minus the number of particles times the partial derivative of chemical potential in phase 1 with respect to temperature at constant pressure. Since we are still in phase 1, all particles are in phase 1, so the number of particles in phase 1 equals the total number of particles. So that's why I don't have N1 here, but I write N, the total number of particles. N1 equals N, equals the total number of particles. Then let's go to point 2, where again we can calculate the entropy from the free enthalpy by taking the partial derivative with respect to temperature at constant pressure. But now we have to use the free enthalpy G2 of phase 2. It's a different function. And same argument as before. Now all the particles are in phase 2. The number of particles in phase 2 equals the total number of particles, which is a constant. So I get this constant factor minus n, total of number of particles, times the partial of the chemical potential in phase 2 with respect to temperature at constant pressure. These two entropies need not be equal. We have, in general, we may have a difference between these two entropies. And let's look at this entropy difference. Delta S. This is S2 minus S1. So we cross the coexistence curve. We go from point 1 to point 2. And at these 2 points, we have different entropies, and their difference is this delta S. We can use the results that we just obtained and find that this is the total number of particles times the difference of the partial derivatives of chemical potential in phase 1 minus the partial derivative in phase 2. And both partial derivatives are taken at constant pressure, and this constant pressure equals this critical pressure P star at the temperature T0. Now, the chemical potentials of the two phases, mu1 and mu2, these are different functions. We know the coexistence condition is that on the coexistence curve, the two chemical potentials are equal, so mu1 is equal to mu2, but their partial derivatives with respect to temperature need not be equal. So inside this bracket, this difference of partial derivatives, this need not be 0. So when we look at the entropy as a function of temperature, as we go along this green line, then let's say first we are in phase 1 and we have this continuous, entropy is a continuous function of temperature, and then we reach the temperature T0 at which the phase transition happens. And the point 1 in the upper diagram, this is the point here just before the phase transition. Yeah, so this is associated with this point is S1. Now at the phase transition, as I said, there's no reason why the two chemical potentials mu1 and mu2 should have, these two functions, should have the same derivatives with respect to temperature. So in general, this bracket may be non-zero, and therefore the delta S may be non-zero. And in this case, you have a jump here. And right after the phase transition, you are at this point 2, and you have the entropy S2, and their difference is the delta S. And then in phase 2, the entropy is once again a continuous function of temperature, so the curve may continue like that. But in general, you may have at the phase transition a discontinuity, you may have a discrete jump in entropy. All of this happens at constant pressure, the pressure being equal to P star at T0. Now I want to stress that there may be a discrete jump in entropies, so the delta S may be different from 0, but it doesn't always have to be. Yeah? So you can have phase transitions at which the delta S does not make a discrete jump. So this is a possibility, but it's not a necessity that at a phase transition the delta S is different from 0. But if it is different from 0, so if delta S is different from 0, then it is clear that for the phase transition to occur, you require heat. You remember the infinitesimal amount of heat, delta Q is TdS, or a finite, sort of the finite version is a delta Q, the amount of heat that you require, is T times delta S. So in order to go from phase 1 to phase 2, you require an amount of heat which is equal to this transition temperature, T naught, times delta S, times this difference in entropy. So if this delta S is different from 0, then the phase transition requires heat, and this is called the latent heat, QL. And this equals the temperature at which the transition occurs times this discrete change in entropy, delta S. And whenever you have a phase transition that requires latent heat, so that involves a discrete change, a discontinuous change in entropy, then this is called a first order phase transition. An immediate consequence of this discrete jump of entropy, another immediate consequence of that, is that when you consider the specific heat, the behavior of the specific heat at the phase transition, and we are working here at constant pressure, so we should consider the specific heat at constant pressure. Remember its definition, that's temperature over particle number times the partial of entropy with respect to temperature at fixed pressure and particle number. When the entropy as a function of temperature that you see on in the left diagram makes a discrete step at T naught, then this derivative with respect to temperature diverges. So this diverges at the transition temperature T naught. And we had already discussed that a finite specific heat and also a finite compressibility are prerequisites for stability, for thermodynamic stability. So conversely, whenever the specific heat diverges or the compressibility diverges, then this is a signature of instability. And this makes perfect sense because at the phase transition, we have spontaneously a system that decomposes into two different phases. So it's no longer homogeneous, and that's a sign of instability. Yeah? So this is this divergence of the specific heat is a signature of instability at the phase transition. Not only the entropy can have a discrete change at the phase transition, but also the volume. You all know when water evaporates that, of course, the vapor takes a much larger volume than the water. And this holds generally for first order phase transitions, that the two phases have different densities and take different volumes. And so you expect that when you go from one phase to the other, you expect a change in volume as well. And let's look at this mathematically and see where this discrete change of volume comes from. Let's again start from the PT diagram with the coexistence curve, phase 1 above and phase 2 below. And let's again cross the coexistence curve, but this time not at constant pressure, but at constant temperature. So let's take a temperature T0, and let's consider this process here, where we move upwards vertically, and we cross the coexistence curve at constant temperature T0. What we vary is the pressure. And once again, let's look at 2 points on this vertical green line, one just before and one just after crossing the coexistence curve. Let me denote this point after crossing the coexistence curve. Let me call this the point 1, because then we are in phase 1, and the point just below, point 2, because we are in phase 2. And let's now consider the volumes at these 2 points. The volume at the first point, at point 1, volume is the variable conjugate to pressure. So we have to take the partial derivative of the free enthalpy with respect to pressure. And this time it's a positive sign. So this is the partial of G1, so the free enthalpy function referring to the phase 1, describing phase 1, with respect to pressure at constant temperature. Once again, free enthalpy is just particle number times chemical potential. We are in phase 1, so the particle number equals the total particle number, which is constant. It's like a constant factor. And we only have the partial derivative of the chemical potential with respect to pressure at fixed temperature T. And likewise, we have a formula for V2. I don't write it out here, but it's the same formula, only with the chemical potential of phase 2. And once again, we can look at the difference of volumes, delta V, V2 minus V1. This is the number of particles times the difference in the partial derivatives of entropy with respect to pressure. So first in phase 2 minus this partial in phase 1. And all of this at constant temperature equal to T0. Now let's look at the dependence of volume on pressure as we move along the green vertical line in the direction indicated by the arrow. So we're going upwards. Yeah? So we are first in phase 2, and then we cross the coexistence curve, and then we are in phase 1. And in doing so, the temperature is fixed at T0. So first we are in phase 2, and then at a certain pressure, which is P star of T0. Yeah, so here I can show it here as well. At the phase transition we have P star of T0. At this pressure, the volume may change by this delta V. And the same argument applies as in the case of the entropy. There's no reason why the two chemical potentials, mu1 and mu2, they are different functions of temperature and pressure. And while the chemical potentials themselves have to be equal at the coexistence curve, there's no reason why their derivatives should also be equal. So in general, there's a bracket, this difference of partial derivatives may be non-zero, and therefore the delta V may be non-zero. And if that is the case, then we have a discrete jump here of the volume. We may jump, in this case, we may jump down, and this difference here, that is minus delta V. And just before the phase transition, we are at this point 2, and just after the phase transition, we are at the point that we labeled 1. Before we are in phase 2, and then we are in phase 1, and V2 minus V1, that is the delta V, but since we're going from left to right, the jump is then minus delta V. Once again, this discrete change of volume may occur at a phase transition, but it doesn't necessarily have to occur at a phase transition. If it occurs, so if the delta V is different from 0, then once again, this is a signature of a first order phase transition. So only in first order phase transition this may happen, that you have discrete changes of volume. And we can look at the compressibility, the isothermal compressibility, kappa T. Remember its definition. This is minus 1 over volume times the partial derivative of volume with respect to pressure at constant temperature and also constant particle number. When you look at this curve, you see, well, if there's a discrete jump of the volume as a function of pressure, then at the phase transition, this derivative diverges. And so the compressibility diverges. And once again, this is a signature of instability. It violates, at the phase transition, compressibility diverges, and this violates our stability criteria. And we have a signature of instability. We had looked at the possible discrete change of entropy at a phase transition and the possible discrete change of volume at a first order phase transition. In fact, these two are related, and they are related by the so-called Clausius-Clapeyron relation. And in order to derive this relation, consider, again, in the PT plane with coexistence curve P star of t, consider in this plane a cyclic process, an infinitesimal closed cycle of the following form. Let's say we start here, and then we move along the coexistence curve, just above the coexistence curve. This is our first step in this cyclic process. So in this first step, we are still completely in phase 1. Then we cross the coexistence curve. This is our step B. Then we move back along the coexistence curve, but just below the coexistence curve. This is our step C. And we are in phase 2. And then finally, in the last step, step D, we cross once more the coexistence curve, and we are back to the point where we started. Initially, we have a certain temperature, then at the right end of the process we have another temperature, and we want to make this cycle really an an infinitesimal cycle, so we assume that the temperature difference here, that this is small. And to indicate that, let me use this infinitesimal notation. So this is a very small, that's a tiny temperature difference dt. And on the vertical axis, we have initially this pressure, and then later, after the first step in the process, we have a slightly higher pressure, and the pressure difference, once again, is very small, and I indicate this with this infinitesimal notation. That's dP. Now let's consider how the free enthalpy changes in each step of the process. Let's consider the first step, step A. The free enthalpy is a function of temperature and pressure. We change as we move along this section A. We change both pressure and temperature infinitesimally, and therefore also the free enthalpy will change by an infinitesimal amount. And this change is given by the partial of free enthalpy with respect to temperature times dt. And since in this first step we are still completely in phase 1, we are above the coexistence curve, we have to use the free enthalpy G1 that relates to phase 1. And then we have a change in pressure, so we have another contribution, that's the partial of G1 with respect to pressure times variation of pressure, dP. So this is the change of free enthalpy in the first step. In the second step, you really have to consider the limit where we are arbitrarily close to the coexistence curve, either from above or from below. So this step B in this limit, there's no distance here in the PT diagram, and the free enthalpy is continuous at the coexistence curve. And therefore, in this limit where we approach from both sides, we approach the coexistence curve arbitrarily close, the change of free enthalpy is 0. There's no change at all. Then the third step, step C, once again we change temperature and pressure, and then there is an associated change in free enthalpy. We're going the opposite direction, therefore we get a minus sign, and we are now in phase 2, so we have to take the partial derivatives of the free enthalpy in phase 2. So we have to use G2 and take the partial with respect to temperature times dt and the partial with respect to pressure times dP. And then the final step, D, where we cross once more the coexistence curve, once again in the limit where we are arbitrarily close from both sides, there is no change of free enthalpy involved. So what is the net change of free enthalpy? It's obviously the sum of these contributions, but it has to be, the net change of free enthalpy has to be 0, because we are back at the starting point, and of course we must have the same free enthalpy as before. So we should sum the various contributions from the various steps and then impose the condition that the total change along this closed loop must be equal to 0. Now if I group the terms that are proportional to dt and the terms that are proportional to dp, I find that the partial G1 with respect to temperature minus the partial of G2 with respect to temperature times dt plus the partial of G1 with respect to pressure minus the partial of G2 with respect to pressure times dp, that this must be equal to 0. We can identify the partial of G1 with respect to temperature, that's the conjugate of temperature, that's minus the entropy in phase 1. The partial of G2 with respect to temperature, that's minus the entropy in phase 2. The partial of G1 with respect to pressure, that's the volume in phase 1. This is the volume in phase 2. Now we take the difference here. So minus S1 minus S2, that's delta S. It's S2 minus S1, that's delta S. And here we have V1 minus V2, and this is minus delta volume. Then the dP, the differential of pressure, now since we are moving along the coexistence curve, dP is related to dt. The differential of pressure is related to the differential of temperature. It's related by the slope of the coexistence curve. So this dP is equal to the slope of the coexistence curve, this is the slope, times dt. So in this form, this condition implies that delta S minus delta volume times the slope of the coexistence curve times dt must be equal to 0. So this bracket itself must be equal to 0. And we can solve this condition for the slope of the coexistence curve. And we find that the slope of the coexistence curve, that this must equal delta S over delta volume. We can express the change of entropy delta S in terms of the latent heat, and then this becomes the latent heat divided by temperature times delta volume. And this equation here, this is known as the Clausius-Clapeyron relation. And you see that it relates the discrete change in entropy to the discrete change in volume, and they are related by the slope of the coexistence curve. Now, unless, which would be a very pathological case, unless the slope of the coexistence curve is 0 or infinite, so excluding these pathological cases, if you just take a finite non-zero slope of the coexistence curve, then this implies that whenever delta S is not equal 0, so there's a discrete change in entropy, then delta V must also be different from 0. So there must also be a discrete change in volume, and vice versa. Yeah? So in fact, at the first order phase transition, generally both entropy and volume exhibit a discrete jump at the phase transition. We've already talked quite a bit about first order phase transitions, I would like to give a more general scheme that allows you to classify phase transitions and to assign an order to a phase transition. And then you will also see how this definition of a first order phase transition fits in a more general classification scheme that tells you the order of a phase transition. So, starting point, once again, PT diagram, coexistence curve, and you somehow go from one phase to the other. You cross the coexistence curve. Let's say you have phases 1 and 2. And then phase transitions are classified according to what happens and how various functions behave when you cross, as you cross the coexistence curve. First of all, let's look at the relevant thermodynamic potential. In our case, the free enthalpy. The horizontal axis here is the parameter that parameterizes my green curve above. So depending on the shape of that curve, that could be temperature or pressure or some other parameter parameterizing this curve. And at some parameter value, I cross the coexistence curve. So this is my crossing point. The thermodynamic potential, so here in our case the free enthalpy, is continuous at the crossing. So we are in phase 2. We must use the free enthalpy G2 that relates to the phase 2. And then after I cross into phase 1, after the phase transition, I have another function G1, but they match at the phase transition. They have the same value at the phase transition. So this is continuous, and that's because we had said earlier that the free enthalpy is simply chemical potential times particle number. So G1 is mu1 times particle number, and G2 is mu2 times particle number. And we know the coexistence condition of the two phases is precisely that the chemical potentials are equal at the phase transition, and hence also the free enthalpies must be equal at the phase transition. So the thermodynamic potential is always continuous at the phase transition. Let's next look at thermodynamic variables that you can obtain from your thermodynamic potential by taking a first order partial derivative. So, for example, we looked at the volume, which is the partial derivative of the potential with respect to pressure. And we learned that at a first order phase transition, at the crossing point, this thermodynamic variable may exhibit, or if it's a first order phase transition, then it generally does exhibit a finite jump. So it goes like that, and then there's a discrete jump. So the delta of this thermodynamic variable is different from 0. There's a discontinuity in this thermodynamic variable if it's a first order phase transition. Next, we can move to the next highest order in partial derivatives of the thermodynamic potential. We can look at thermodynamic coefficients which are related to second order partial derivatives of the potential. So, for example, we looked at the specific heat at constant pressure, we looked at the isothermal compressibility, all of these can be obtained from the relevant thermodynamic potential by taking second-order partial derivatives. And we learned that in a first-order phase transition, these thermodynamic coefficients diverge. Now, the figures that I drew, that they relate to a first-order phase transition. And it's called a first-order phase transition because a discontinuity appears for the first time when I take the first derivative of the thermodynamic potential. Yeah, so this is why it's called a first-order phase transition, because the discontinuity appears in the first-order partial derivative or derivatives of the thermodynamic potential. And you can generalize this and define an nth-order phase transition. And an nth-order phase transition is a phase transition where a discontinuity appears, and it appears for the first time in the nth-order derivative or derivatives of the thermodynamic potential. So, specifically, a second-order phase transition. In a second-order phase transition, you do not have a jump in entropy or volume at the phase transition, but you have a discontinuity in certain thermodynamic coefficients. And tomorrow we will look at a specific example for a second-order phase transition. We will look at the Ising model of an anisotropic ferromagnet, and we will see that the entropy is continuous at the phase transition. But there are certain thermodynamic coefficients that are discontinuous at the phase transition. And that's why it's a second-order phase transition. And more generally, an nth-order phase transition is a transition where the discontinuity first appears in the nth-order derivative of the potential.